If you were just asked straight away whether you'd prefer to have a biased estimator or an unbiased estimator, it seems like a silly question, an obvious question to answer, that you would prefer an estimator with no bias or very small bias. But there's a few famous examples of where we can have an unbiased estimator, which is in fact fairly obviously not a good estimator. Because an unbiased estimator only means that the expected value of that estimator is the true value. So it gives the right answer on average. But of course, you can have something which is on average correct if it's sometimes wildly too low, sometimes wildly too high, but on average, those cancel out. So we probably want not just to consider the bias, but also how variable those estimators are, whether they are stable. Now, this is a little bit contrived, but there's a really nice famous example of where an unbiased estimator can be wildly misleading. And this is Basu's elephant. And it comes from a story which says, let's say there's a circus, the circus owns 50 elephants, and they want to know the total mass of all 50 elephants. Circus has done this before. When they did this before, they weighed all 50 elephants, and they knew that one elephant they found in the story is called Sambo. Sambo's mass was pretty much the average of all of the other elephants. So to save a little bit of time and money this time around, they say, let's not bother measuring all of the elephants again. We know that Sambo was about 1/50th of the total mass, therefore we'll just pick Sambo, we'll measure Sambo's mass, and we'll assume that 50 times Sambo's mass is the total mass. Now that seems a very sensible idea. Although statistically speaking, it's not guaranteed to be unbiased. But they call it a statistician. Not a very good statistician. This person knows a lot of statistical theory, but sadly doesn't know a lot of common sense. So the statistician says you can't just pick Sambo, that's not a random sample. You should pick a random sample and work out an unbiased estimator. And the statistician says, well, if you pick one elephant and you pick an elephant with probability, you pick elephant J with probability Pj, measure the mass omega J of the elephant you've picked, and that omega J divided by the selection probability Pj will be an unbiased estimator of omega total, the total of all 50 elephants. Now, the circus owner knows that they now have an unbiased estimator, and they think that picking Sambo's the best idea. So they've got to do some randomization, but they decide that what they will do is they will pick Sambo with probability 99%, and with probability 1%, they'll pick one of the other 49 elephants, each with equal probability. So the circus owners are thinking, well, I'm definitely going to pick, or not definitely, but close to definitely going to pick a really representative elephant to put into my unbiased estimator, so I'll get a good estimate. Introducing a little bit of notation here, we've got an indicator variable. So I subscript j just takes the value 0 if we don't select elephant j, and the value 1 if we do select elephant j. So I've got 50 of these indicator variables for the 50 elephants. So 49 of these indicator variables will be zeros, and one of them will be a 1. So what this means is if I want to work out the expected value of my estimator of omega total. That's the expected value of omega j divided by pj. Now I can bring in the indicator variables here, because omega 1 times I1 over P1 is going to be either this omega j over Pj, if j is 1, and 0 otherwise, and so on. So I've expanded this one term. Rather than just having the jth term, I've got all 50 terms, although 49 of them will have a 0, will be multiplied by 0, so will disappear. So it'll be left with the same thing. But the critical thing here is asking, what's the expected value of each indicator variable? Well, each indicator variable is a 0 or a 1, so its expected value is just the probability that it is a 1, the probability that I pick elephant j, so it's pj. So, in other words, what I'm left with is I'm left with the expected value of omega 1 p1 over p1 plus omega 2 p2 over p2, and so on. So you can see that all of these selection probabilities on the top and the bottom will cancel out. What I'll be left with is the omega total. So this is an unbiased estimator, as the statistician claimed. But the problem is that if I apply this to the circus owner's selection strategy, which gave a 99% chance of picking Sambo, then rather than saying Sambo is an average elephant, I have 50 elephants, so my best guess of the total body mass is 50 times Sambo's mass. I'm left with this weird division of Sambo's mass by 0.99, or the 99% selection probability. So in other words, I'm claiming that my unbiased estimator is 100 over 99 times Sambo's weight. So the other 49 elephants would be weighing 1/99th of Sambo's weight. That's wildly ridiculous. Even more absurd if I think of the case, let's say I pick the heaviest elephant as the one selected. Well, in that case, I only had a 1 in 100 chance of not picking Sambo, and I only had a 1 in 49 chance then of picking the heaviest one from the other 49. So in fact, in this case, I would estimate that the total mass of the elephants is 4,900 times Jumbo's weight, where Jumbo is the heaviest elephant. So this clearly is even more absurd. But it's unbiased. So how is it unbiased? Well, it's unbiased because if I pick Sambo, I have a ridiculous underestimate of the total. And if I pick another elephant, I get a ridiculous overestimate of the total. But on average, it's right. It's also completely and utterly useless. So it's a good example of the fact that an unbiased estimator is not necessarily a good one if it can be wildly inaccurate in either direction. So this is a bit contrived, but famous example from Basu, the Bangladeshi Indian survey statistician.